Hi there, and welcome to this presentation for the IGDIM 2020 online conference. In this presentation, I will try to convince you that X-ray absorption spectroscopy is an ideal tool to probe electron transfer processes in luminescent materials. This work was largely performed at the Lumilab research group at Ghent University in collaboration with the ESRF synchrotron facility in Grenoble, France. If, when seeing this presentation, you want to drop me a line or have specific questions, you can find here my contact details. Here you can see a typical example of an application of inorganic luminescent material, or phosphors as they are commonly called, namely in solid-state lighting, where the blue light of LEDs is converted to longer wavelengths by means of luminescent materials. On the bottom you can see a number of phosphors that all contain the europium-2+ ion as an active center, but where the emission color is driven by the composition of the host compound. In this presentation I will focus on bluish-green emitting materials where the host is composed of strontium aluminates. Now, if we take a look at what happens in those compounds, we have our europium-2+ luminescent center. We have an excited state, which is a 5D state in this case. When blue or UV light is falling onto the phosphor and being absorbed by the europium-2+ center, then an electron can go to the excited state, and typically within microseconds this electron returns to the ground state, and then a blue or a green photon can be emitted. A specific class of luminescent materials are persistent phosphors. Those phosphors contain additional defects besides the luminescent center, what we call traps. And those traps have the possibility to trap this electron from the excited state. And this electron can remain there for quite some time. Only if the energy barrier which exists to return to the ground state, to the excited state, is overcome, then the electron will be released from the trap. So we have in general an energy barrier here that you need to overcome to release the trapped charge. Now, this barrier can be overcome by different means. You can use light to do this. Very often this is infrared or red light. You can use pressure, and in that case we call it mechanoluminescence, but we can also use heat, and in this case we call it thermoluminescence. If we perform this experiment at a fixed temperature and we look at the light output, then we will see that as a function of time, initially there are many trapped electrons, the intensity is high, and then it decays in an exponential way. Now, question is, what are those traps? They are defects, but are they associated with lattice defects? For instance, in strontium aluminates, oxygen vacancies play a very important role. But we also know that the intensity of the afterglow is strongly influenced if we add dysprosium 3+ to the phosphor composition. Now the question is this center itself trapping the charge, or does the introduction of the dysprosium 3+ lead to additional lattice defects? All the details about the work I will present here can be found in this very recent publication. To study whether the dysprosium is indeed an electron trap, we performed XANES experiments at the ESRF facility in France, and more specifically at the ID26 beamline. Now, the advantage there is that we can, for the X-ray absorption spectroscopy, we actually look at the fluorescence of the element we are investigating, where we can also filter on the emission energy, which leads to very well-defined absorption between quotes, spectra. Now, if we look at a typical example here on the right, you can see that two peaks are present. The first peak, the so-called white line, is related to divalent europium. The second peak is related to trivalent europium. So we have here a tool that can make a distinction between divalent and trivalent lanthanide ions. At this beamline, we, however, have a very high X-ray intensity, which is also concentrated in a relatively small spot size. This has two effects. First of all, the X-rays can also charge the sample. By this, we mean that the X-rays can fill the traps with electrons, and so it's very difficult to study the initial state of a phosphor where there are no filled traps. Secondly, when we measure for extended times, we can clearly see that there is a beam damage going on in this very small spot. So this limits the reproducibility of our experiments, and we should always take care that we are looking at the real underlying luminescence processes and not at degradation processes. The solution was to mount a pallet of the phosphor we are going to investigate, so strontium aluminate doped with europium and dysprosium, and we mounted this on a computer fan which could be which we could spin very rapidly at about 2,700 revolutions per minute. Now the advantage is when we put the beam towards the edge of the pallet, that because it's rotating rapidly, we spread the beam out over a large circle with a circumference which is very significant compared to the height of the X-ray beam. Now, if we take a look with a camera to what is happening when such a sample is spinning and we switch on the beam, then we see several things occurring. So the X-ray beam causes first a very strong yellow emission, and then we see a blue circle appearing with an intensity that is building up during on the order of tens of seconds. So you clearly see that the circle gets fully illuminated. Given the very short decay time, luminescence decay time of the europium center itself, this is a clear indication that we are filling traps because the blue circle is caused by release from previously trapped electrons. If we first take snapshots from this video, we see that when we switch on the beam, that we get this comet-like tail we have in yellow emission. This is caused by the dysprosium emission with a fairly long luminescence lifetime. And then when time proceeds, we clearly see that a circle is appearing, which is homogeneously illuminate or gives homogeneously blue light with a fairly constant intensity over the entire circle. When we switch off the beam, we see that there's a clear afterglow and this circle remains visible for a very long time. The blue-green you see here on the first images is just an artifact from the camera taking the images. The advantage is, of course, that when we have the sample here on the right, that we can add not just a camera, but also a spectrometer, which can provide us with the luminescent spectra at different positions. So here you see an example. In spot 1, we mainly have initially the dysprosium 3+ emission, which is very prominent here just beside the X-ray beam in the beginning. And then for position 3, we mainly have the bluish-green emission, like you can see here, for the europium 2+ ion, so the persistent luminescence we are observing. This we can now combine with the time evolution when we switch on the electron beam. And then we clearly see with the spectrometer that there is a buildup in the europium 2+ emission intensity, which lasts about 30 seconds. The dysprosium 3+ emission is essentially stable, although one can see that there's a limited drop in the beginning of the profile. Now, at the same time, we can also monitor the white lines for the europium 2 plus and 3 plus white lines, as well as for the dysprosium 2 plus, which is positioned here, and the dysprosium 3 plus. When we do this, we get the following plot. So if you monitor the white line for the europium 2 plus, the blue dots, then we see a decrease. Very importantly, this decrease occurs on the same time scale as the buildup in the afterglow, which is proportional to the buildup in charges which are trapped at the different defects. At the same time, the europium 3 plus signal is increasing. If we now look at the white line for dysprosium, then we see that there's a small drop in the number of dysprosium 3 plus ions, and at the same time, the dysprosium 2 plus, the green symbols, are increasing. So we can clearly say that we have a redox process going on where an electron is transferred from the europium ion and is trapped at the dysprosium ion, forming a divalent dysprosium species. So in principle, we already have here some evidence that indeed the electron transfer is occurring, but we are looking at specific X-ray energies. What we would like to have is also very detailed Xenes spectra to see the evolution in detail. And this we can do by making some kind of a pump-probe experiment where the probe is the X-ray beam. And we know that those X-rays are filling the traps, but we have other means to fill the traps and to empty the traps. If we add a blue or a near UV light source, we will pump more europium 2 plus ions, and so more electrons will go to the traps. If we, on the other hand, add more stimulating light with a long wavelength, infrared light or red light, then you will have that this light can detrap previously trapped electrons. So we can shift the equilibrium to the left and empty preferentially all those traps. In this way, we have an optical pump to drive the number of trapped electrons, while the X-rays will only have a minor influence. In this setup, you can see the situation where we have LEDs here in the middle pointing at the sample, which is just behind the fan here. And then we can add additional light sources, which are coming from below and above the path of the X-ray beam, which is sitting here in the middle. And this is the result. If we switch on the infrared light, we get the dashed lines, which means that we have very limited number of traps being filled. And you can see that you have a slightly higher europium 2 plus signal than europium 3 plus signal. There is a little bit of dysprosium 2 plus, but it's fairly limited. If we now switch on the blue light, then we will start the transfer process from the europium to the dysprosium, and we easily see that the signal in europium 2 plus is dropping, europium 3 plus is increasing, dysprosium 2 plus increases, dysprosium 3 plus decreases. On the bottom you can find the difference plots between the two states with empty traps and filled traps. And there you can easily see that you have this transfer process. And so this strategy can further be extended to look at more details of both the Xenes and possibly also the XF's region, because we can now put the phosphor in a specific state. Based on those experiments, those Xene spectra for the two states with maximum filled traps and almost no filled traps, we can derive that about 3% of the europium ions are participating in the trapping process. On the one hand, this is very good news because it means that we could try to enhance this fraction to have a larger storage capacity for the phosphor. On the other hand, if we look at the time evolution of the luminescence, we have to conclude that essentially all of the europium ions are already participating to the trapping process. So those two observations with apparently contradicting results, we have to look at it in more detail. Now, one way to do this is to really count how many photons are emitted by a certain material to determine an absolute storage capacity instead of a relative measurement. If you follow the procedure in this paper, then you will find that the trapping capacity is determined by only a few percent of the number of europium-2+ ions, which is totally consistent with the Zane's experiment. But how can we then explain why all europium ions are participating in the trapping process? A clue is found if we look very carefully at the quantum efficiency of this particular phosphor. So the quantum efficiency is the number of emitted photons divided by the number of absorbed photons. And in principle, you expect this to be independent of the excitation intensity, as long as the excitation intensity does not become too high. Now, what you can see here is that initially for very low excitation intensities, this value is very high. And when it drops, it becomes, when the excitation intensity increases, the quantum efficiency drops. And this can be explained by the different processes. Because if we go back to our drawing with the different energy levels, then we know that this trapped electron can also be released by red light or infrared light, but it can also be released by means of UV or the blue light, the same light we are using to excite our europium-2+ ions. So if this happens and an electron is released when, again, blue or UV light is coming in, then this electron can still go to the previously ionized europium ion and gives us emission. Now, the problem is that we have first used one UV photon to excite our europium ion, which then leads to trapping. And then we need a second high energy photon to release this trapped charge and then have the recombination. So for one photon that eventually comes out of this phosphor, we need to invest two photons. And this will cause not only the quantum efficiency to drop once we are detrapping more of those trapped electrons, but it's also reflected if we look at the optical absorption, which increases if we increase the excitation intensity. And from this profile, we can derive that the trapping cross-section of the defect of the traps is actually larger than the trapping cross-section of the europium ions. If we make a schematic drawing, in this case we have all the europium ions being in the ground state, all the traps are empty. If we now absorb a blue photon, some of the traps will be filled and afterwards they can be released, the trap charges, and we can have emission. But this situation where we have filled all the traps does not occur. And this is due to this optically stimulated detrapping, because the traps will have a fairly large absorption cross-section indicated here by the red circles. So as soon as a number of those traps are filled, an incoming blue photon will have a higher probability to lead to detrapping than to create another trapped electron. As this is a 2-for-1 process, you have to invest 2 photons to get 1 out eventually. This is not a very efficient process, but it also limits the trapping capacity of those persistent phosphors. So in conclusion, I hope I have convinced you that X-ray absorption methods, spectroscopy methods and phosphors are a great match, provided that we avoid beam damage and that we consider experiments that offer us as much information from the X-ray side as from the luminescence side. If we look at a lot of co-doped persistent phosphors, which very often contain europium plus another lanthanide, then the trapping is to a large extent driven by a redox process where an electron from the europium ion is trapped at the trivalent dysprosium in this case. We can also bring all the numbers on the trapping capacity and the participation of all the ions into play if we consider an optically stimulated luminescence or an optically stimulated detrapping process into play. Now, this sounds a little bit depressing, but because it would mean that there is some fundamental limit on how efficient you can make persistent phosphors. But on the other hand, it's clear that the optical signature of the trap will determine how strong it will absorb or how strong it will compete with the europium ions when there are incident blue or UV photons. So by designing different trapping defects with different optical signatures, we might further enhance the storage capacity of persistent phosphors. So we could look at other defects, and I think that's clearly the road ahead for this type of research. I thank you for watching this presentation, and feel free to send me some feedback. More presentations can be found at this SlideShare site. Thank you.